Good afternoon, everybody. Hope you're all healthy and safe at home. Let us continue with our section, Chapter 2, Hilbert spaces. Now, in the previous lecture, we had done the inequality called Bessel's inequality. Now, what we are going to do is we are moving on to a new definition. It is about the concept of complete system. So, when do we call a system to be complete? Let's see the definition. A system xi where I greater than equal to 1 is said to be complete system if the linear span, that is the set summation I equal to 1 to n alpha I xi for every n and every scalars alpha I of the vectors set xi is dense in x. So don't get confused. It's just that a system set xi is said to be complete if span of set xi is dense in x. Okay, that is all possible linear combination of elements of xi must be dense in the space x. Then we say that that particular system is a complete system. Now we'll move on to few notes which you have to keep in mind. There is a theorem called the Weierstrass approximation theorem. We're not going to the proof of that theorem. It's just a theorem which you have to know. You can refer any textbook of functional analysis and you will get the proof of this theorem in the textbook of LEMMA and all. The Weierstrass approximation theorem states that the polynomials are dense in the space C of 0, 1, set of all continuous functions from 0 to. Or in other words, we can say that the system t raised to n, this is the basic form of polynomials, right? When n is 0, we'll get t raised to 0, that is 1. Then we get t square, t cube, and so on. So that is the basic system of the polynomials. So we can also say that set t raised to n, or this system, is complete in C of 0, 1. Why? Because using approximation theorem we can say polynomials are dense, and this is the system of polynomials, or using this the linear span will be polynomials, right? That is, this system set t raised to n is complete in C of 0, 1. Now by the definition of L2 of 0, 1, that is space L2, we know that L2 of C 0, 1 is the completion of C of 0, 1. So we can say that L2 of 0, 1 is dense in C of 0, 1. And since polynomials are dense in C of 0, 1 and L2 of 0, 1 is again dense in C of 0, 1, we can conclude that the polynomials will be dense in L2 of 0, 1. So that is the interconnection between the space C of 0, 1 and L2 of 0, 1. I hope that picture is clear with you people. Now similarly, the Weierstrass approximation theorem also states that the trigonometric polynomials with the periodic function 2 pi, here the periodic function of this interval is 2 pi, right? So the Weierstrass approximation theorem also states that the trigonometric polynomials are also dense in C of minus pi, close interval minus pi. So again, like we had done in the previous note, we can say that since the polynomials are dense in C of minus 1 minus pi, we can say that the trigonometric polynomials are dense in L2 of minus pi, right? And in the previous case, we had considered the system t raised to n. So here we are dealing with trigonometric polynomials. So the system will be set 1, cos nx, sin nx. The linear combination of all these terms will give all the trigonometric polynomials for us. So this set is complete in L2 of minus pi. So just keep this in mind, or you can also see whether this is true or not. You can easily verify it. Now next we'll move on to a lemma 2.1.6. The lemma states that if set fi is a complete system in a Hilbert space H and x is orthogonal to fi for every I, then x must be 0. So if there is an element which is orthogonal to every member of a complete system, that particular element must be 0. This is the concept behind this lemma. So let's see how we can do the proof of this lemma. First we have to consider a complete system given to us is set Fi is complete. So if this system is complete, by the definition we can say that summation I equal to 1 to n alpha I Fi for every n belongs to n and for every scalar alpha I is dense in the space H, right? Or in other words, as I had mentioned, we can write span of the set Fi is dense in the Hilbert space H. So this is given to us. Also it is given that X is orthogonal to Fi, right, for every I. Now if X is orthogonal to Fi for every I, this implies, what can we say? We can say that X is orthogonal to span of Fi, right? It will be orthogonal to every linear combination also, right? See, if inner product X F1 I'm sorry, this is X, inner product X F1 is equal to 0 and say inner product X F2 is again 0 because X is orthogonal to Fi for every I, then I can easily say that inner product X F1 plus F2 is also 0. Why? This is because this can be written as inner product X F1 plus inner product X F2, right? So if it is orthogonal to Fi for every I, then it will be orthogonal to span of Fi also. Now we had seen that since the set Fi is complete, span of Fi is dense in H. So from this we can conclude that X is orthogonal to a dense set in the space H, right? Now if X is orthogonal to a dense space, dense set, we can always find, therefore we can find a sequence, say Xn in H such that Xn converges to the element X and Xn is orthogonal to X for every n. Okay, since the set X is orthogonal to span to a dense set in H, we can always find a sequence Xn such that Xn converges to this point and also Xn will be orthogonal to X. Okay, now if Xn is orthogonal to X, what we can say? We can say that inner product Xn X will be 0, right? Now we know that inner product is a continuous function, right? We had proved that. We know that the inner product is continuous. So as it is continuous, inner product Xn X will converge to inner product Xx, right? Since the inner product is continuous and Xn converges to X, we can say that inner product Xn X converges to inner product Xx. So from this we can say that what is inner product Xn X? We had said that it is 0. And what is inner product Xx? This is nothing but relation between inner product and norm. This will be norm X square. So we can conclude that norm X square tends to 0. So, or we can say that norm X will be 0, and from this we obtain that x has to be 0 by the property of no. So the proof was very simple. We just had to consider the definition of the complete system. So just go through the proof of this lemma once again, and I hope you will be clear with it. So with this we shall wind up our section. Thank you. Stay home and stay safe.